Let's share our screen. Let's do that. Let's, man. All right. Okay, sorry. So we started chapter 4. Let me remind you what we were doing. So chapter 4, number theory or arithmetic means the same thing. Arithmetic and cryptography. Again, the motivation, or one of the motivations, is that we're going to see in detail the RSA public key cryptography protocol, which is based on some moderately advanced number theory. So we need to develop this number theory before we see that, okay? Last time we saw briefly the division algorithm, or so-called division algorithm. Let me remind you very briefly what this is about. Okay, but first, yeah, just a couple of things. We defined the notion of divisibility. So we say that A divides B, right? If B is a multiple, these are all integers. We're looking at only integers here. So A divides B if there exists a K such that AK equals to B, right? So B is a multiple of A is a divisor of B, A divides B. That's a notation right there. Fact, which we will use constantly, and is, if you think about it a few seconds, it's clear, right? But so if A divides B and A divides C, then A divides KB plus LC for any integer. So it means that if you divide two numbers, these are all integers, you divide two numbers, you can take any combination of these two numbers. So you multiply one by something, you multiply the second by something else, you add them together, you will still have a multiple of A. All right, so we're going to be using this repeatedly. So what's the division algorithm? We saw that last time. Again, it's called an algorithm, but it's not actually an algorithm. The name comes from the fact that we use an algorithm to divide to obtain the result of the theorem that the theorem says exist, which is this: if you take any positive integer and you take any integer, so I take a D, which is a integer greater or equal to 1, I take any integer A, then I can write A as follows: there exists unique, and the uniqueness is fundamental. Yeah, so I write uniqueness. There exists unique Q and R such that A is equal to QD plus R, where if I just leave it like that, then it's okay, I should, sorry. Let's put this here, just in case. Okay, so if I just leave it like the way I wrote it there, it's not true. So where does the uniqueness come is from the fact that R is between 0 and D. Okay, so R is greater or equal to 0 and strictly less than D, and these numbers are unique. Okay, so I actually did a proof of this last time, but I think that once you know what this is talking about, it's natural, it makes sense, right? So you take any integer A, you divide it by D, right? And there's going to be a remainder, right? If your remainder is too big when you're dividing, then you can still remove some D's from your A, and then so Okay, so for example, just to illustrate, I am going to use the same example I used last time, I guess. If you use a equals to 50 and d is, say, 4, then you look at how many 4s you can fit into 50, so that's 12, right? So 50 is 12 times 4, and there's 2 left. So this is your Q and this is your R, and they are unique, okay? All right. So this defines two functions. Okay, now we're going to come to a place where somehow everybody, not everybody, but a lot of people get confused and messed up. And I'm going to try my best to not confuse you or mess you up, okay? But I'm going to define two functions, and then I'm going to define a relation. And unfortunately, the notation for a couple of these things is similar, but there are different things, okay? So let's try to clear this up. Okay, so I've got the number A, I've got the number D, and I can, from those two numbers, I find these numbers Q and R, which are unique. So this actually defines a pair of functions. Okay, so you give me A and D, and I can return Q and I can return R. Okay, so this defines two functions, which you may have seen before. They exist in most standard programming languages, so you may have used them before. That's possible. So here are the functions. So let's see if I can. Yeah, let's go here. Sorry. Okay. So definition. Okay. So two functions, mod and div. So these two functions, let's not do it too formally. I'm just going to write this. Okay. So two functions. Okay. These functions go from z times z plus to z. Okay, what's z plus? It's positive integers. Okay, so the input would be any integer a and any positive integer d, and the output for this pair would be the number, let's say q, okay, that we found from the division algorithm. And the other one, so that's two functions with A and D as input, it'll return R from the division algorithm. Okay, and so the theorem tells you that these are well defined. So given any such A and D, there is a value and it is unique. There is only one. Okay, so these are well defined functions. The notation varies. I'm going to use the one from the book. So the Q will be A div D. I'm underlying it. You might, in the book, I think it's probably bold font, okay? And the R we will call A mod D, which is the one which creates so much confusion. Okay, because we're going to use MOD for something different in just a sec. Similar, but different, okay? So these are your two functions, which are mod and div. Okay, so they just return those two numbers from the division algorithm. Okay, so again, same example. I had 50 equals to 12 times 4 plus 2. When I divide 50 by 4, I get a remainder of 2, and I need to multiply 4 by 12. So here it means that 50 div 4 is 12. And 50 mod 4 is 2. Okay. All right. Here's an observation to connect to another function. Observation. Okay. So when I'm dividing 50 by 4, right? What I'm trying to do is to fit as many 4s in 50 as I can, right? So I'm just going to use the example, and then I'll move on to the general case. So note here, 12 is the largest number, let's say k, integer, right? Such that k times 4 is still less or equal to 50. Does everybody believe what I just said? That's what we do, right? So you look at how many times you can multiply 4 to reach 50 but not go over, right? And once you've reached that maximum value, you look at what's left, and it has to be less than 4, because otherwise you could have moved one step further, okay? So 12, this q here, so q is the largest integer such that q times d is less or equal to a. That's in, I'm just repeating what I just said, but not in the example, but in general, right? In other words, this q, what is that? This is floor of a divided by d, okay? So that's another way of expressing that function div, okay? So a div d is the same as floor of a divided by d, okay? So these are two different ways of writing exactly the same thing, okay? If you have questions, please do not hesitate anytime. Am I recording this? Yes, I guess I am. I am. Oops, sorry. Okay. What did I want to say next? Yes. So let me try to give you still more intuition about this whole business. Let's try to connect this to other stuff. Okay. So I don't want to do that. Sorry. Okay. Still more intuition, because we're going to play with in this context a lot. Okay. Intuition about this. Okay, so let's take, for example, let's take d equals to, I'll take 4 again. Okay, yeah, 4. Okay, so I'm interested in looking at what happens when I take any integer a and to find those q and r. Okay, so let's list some integers here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, so on, -1, -2. So these are my values for a. Okay. And I'm going to look at the value. So d is fixed at 4, right? So I'm looking for q and r here. Okay. So 0 obviously is 0 times 4 plus 0, right? 1, right? 1, that's 0 times 4 plus 1, not very exciting or surprising. For 2, it's going to be the same, right? 0 and 2. Then 3 is 0 times 4 plus 3. And then when I hit 4, then I go up, of course, 1 times 4 plus 0. So here I go 1 and 0. And then you can probably see the pattern. This will just keep on going. This is 1, 1, 1, 2, 1, 3, and then 2, 0, 2, 1, so on, right? What about if I go to -1? -1, well, I need to express this as something times 4 plus a remainder, which is positive. So this is the only extra little thing that happens with the negatives. You just have to think about it. So you'll need to multiply 4 by -1. So that's -4. And then you're going to add 3 to reach -1, right? So this is like this. So this is -1 and 3, but now you can see the pattern. It'll be the same here, -1 and 2, -1 and 1. For -4, it'll be -1 and 0, and so on. Okay, so let's take a look at these pieces here like that. Okay, and now what I'm going to do is I'm going to draw a circle. Okay, so basically what I'm going to do is to see this as happening on a circle. 0, 1, 2, 3, right? These are my values of R. Okay, and now what I do is I can imagine this happens as follows. So you have your integer a, let's say 6. Okay, let's say I'm considering the number 6. And what I want to do is to go around the circle and see where I'm going to end up if I do 6 steps. So what I'm going to do, of course, is 0, 1, 2, 3, 4, 5, 6, and I'm going to end up right over here, right? And if you look at Q and R, what they're saying, Q says basically it's the number of full circles you're going to have to go around, and then the number of steps to reach your destination. So 1 times the Q here, 1 times 1 full circle, and then 2 steps, right? And of course, if you look at the negatives, it means direction is backwards, right? So that's essentially it. So basically what you're doing is you're taking the whole real line, I mean the integers, and you're wrapping this thing around this circle. So the R is where you end up on this clock. You can see it as a clock with only 4 hours, right? So you see where you're going to end up this way, okay? So that's a useful way of seeing all this, and I'll get back to that a little later. In more generality, okay? But that's another way of seeing this, okay? So let's move here. So this introduces what we call modular arithmetic, okay? Which is another way you can see this if you do a little search, but clock arithmetic, that's the same thing. Not a very fancy way of saying it. In other words, this is the arithmetic of remainders. Okay, let me try to explain, well, why this would be useful. Let's say that you are looking at D equals 2. So one possible motivation, which is an important one, but just to illustrate. Okay, so let's say you have D equals to 7. Okay, so you take the whole real line and you wrap it on a circle which has 7 values like this. Okay, so Z is wrapped on a clock or circle with only 7 possible values. These are your remainders that you're looking at. So you get 0, 1, 2, 3, 4, 5, 6. Right? So if you're dividing any number by 7, you're going to get a remainder between 0 and 6. So you have this infinite number of integers, but if you just look at what happens when you divide by 7, you have 7 possibilities. This is very powerful when you're analyzing, for example, you're looking for solutions to equations. Rather than look at all possible integer values, there are infinitely many of them, you reduce the whole thing. Let's say with D equals to 7, you can choose whichever number you want. And if you can show that there's no solution in that reduced context, then you know there's no general solution, okay? So a standard trick, for example, to show an equation has no solution Z, right, is to reduce modulo, let's say D for some smart choice of D. Okay, so if you're looking at a certain equation, you'd have to check infinitely many values. But if you choose D smartly, you can maybe show that the divisibility in the equation, there's no possible solution that will make it work for that D. And so there can't be any solutions. And you have only finitely many values to check in a sense. Okay, so this is a very standard strategy. I'm giving you one possible motivation for looking at modular arithmetic, but it gives you some idea of the idea of what it might do. Okay, so let's do a couple of definitions. Yep. Okay, let's do a couple of definitions, and this is where the notation, unfortunately, somehow you have to be careful. Okay, so I have two integers, A and B, any integers, and some positive integer, M. Okay, so we're going to say that A and B are congruent modulo M if M divides their difference. Okay, this is our definition. So we say that two integers are congruent mod M or modulo M if M divides their difference. This is notated as follows: A congruent to B mod M. You might see the mod M in parentheses. Notice that I didn't underline M. Okay, it is related to the mod function, but there are different things. It's a notation, so warning. Not the same as the mod function. Okay, so these are different. This is a notation for a relation. This is a relation between pairs of numbers. Right, so it's congruency mod M, congruence mod M. Okay, so it's not a function, right? Okay, so written like that, maybe it's not obvious to you what it means at this point, but what it means is, if you think a little bit about it, if you mess around with it a little bit, you will figure out that what it means is the following. Okay, and for this, I'm going to state it as a theorem immediately. Okay, so if you take any integers, A and B, and any positive integer, then A is congruent to B mod M. If and only if, and this is the connection between the function and the relation, if and only if A mod M is the same as B mod M. Okay, so maybe this is easier to understand. So two integers are congruent mod M means that they have the same remainder on division by M. Okay, so in other words, A congruent to B mod M if and only if they have the same remainder when divided by M. Okay, and I'm going to show you why this is true. So I'll need a little lemma. So I'm not. Oh, this is theorem 3, by the way, in the book, so that you can, if you're looking at the book at the same time, you'll know where this is. Okay. So I'm going to show you why this is true. And for this, I'm going to divide up the proof into two little parts. So my first little part is the following, which is useful in itself. So I'm going to call that a little lemma. Okay. So write A equals to QD plus R, where R is greater or equal to 0 and less than D. In other words, these are the Q and R from the division algorithm. Then I claim that D divides A if and only if R is, most of you can figure it out, 0. Okay, let's prove this. Okay, so I want to say that if I take my integer A and D, integers A and D is greater or equal to 1, then I use the division algorithm to find Q and R. Then D divides A means the same thing as the remainder is 0, which, I mean, if you've been paying attention, you certainly believe this. Okay, this makes sense. But let's just verify it. Okay, so one direction, so it's an if and only if, so there are two directions. One direction is obvious. So if R is 0, then A equals to QD. So D divides A by definition. That's it. Okay. For the other direction, okay, suppose now, so I'm going to write it. Okay, so this is this direction. This is this direction we're using. So this direction, then this direction. So I want to show if D divides A, then R equals to 0. Suppose D divides A. Okay. This, okay. Hopefully you'll believe this or understand what I'm saying. If not, tell me. So suppose D divides A. By definition, this means there exists some, I'll call it K, right? So that we don't confuse with Q. There exists a K such that A equals to K times D, right? So that's what it means for D to divide A. Now, what does the division algorithm say? It says there exists unique numbers Q and R such that you can write A as QD plus R and R is greater or equal to 0, less than D. This has to be it, right? So uniqueness in the division algorithm in that theorem implies that K is Q and R is 0. So R is 0 as desired. Okay, so again, if you use the division algorithm, you look at the Q and R, then D divides A precisely when R is 0. Okay, so that's a special case of what I'm trying to do, but I'm going to use it to prove the whole thing. So the theorem I want to show now is this, that A and B are congruent mod M, which by definition means M divides their difference precisely when they have the same remainder on division by M. Okay, this is what I want to show. Okay, so let's do that. So let's copy this and paste it here. Okay, so here's the proof. By the way, I'm doing these proofs for many reasons. One, because if I'm claiming something, I should convince you. If you say, well, I don't need to be convinced, this is obvious, you should be careful. And the other thing, of course, is that you see by example how I'm doing this, how we're going through this, and we play with the concepts, so it helps to get them in our brain. Okay. Okay, so I want to show, I'm going to do this if and only if in one shot. Okay, so I'm not going to go one direction and the other direction. I'm going to show it in the if and only if in one shot. Okay, so let's do this. So I'm going to need what A mod M and B mod M mean. So what do they mean? Recall this. Okay, so write A equals to Q1M plus R1 by the division algorithm, and write B equals to Q2M plus R2. So these are the numbers given by the division algorithm. Okay, so A mod M is R1 and B mod M is R2. Okay, so R1 is A mod M, R2 is B mod M. Okay, so what do we want to show? We want to show A congruent to B mod M means M divides A minus B. So I want to show that M divides A minus B precisely if R1 equals to R2. This is what I want to show. This is exactly what the theorem states. Okay, so I want to show this. Okay. This is, I'm not going to do the hardest part of the proof, which is not hard, but here it is. Okay. Fact. I hope you all believe this. M divides A minus B if and only if M divides B minus A. Is there anybody who disagrees? No, obviously not. Okay, so the reason is, of course, that if A minus B is a multiple of M, B minus A is minus A minus B, so it's minus whatever you multiplied to get. Yeah. Okay, so hopefully you all believe this. Okay, so M divides A minus B or M divides B minus A means the same thing. Why do I say that? Because I just want to have my R1 and R2 in the right order. So what I mean by this then is that then without, whoops, are you okay with, I don't know if I've used this before, but I'm going to use it here. Without loss of generality. I don't know if I used this abbreviation before. Okay, so without loss of generality, I can assume that R1 is greater or equal to R2. Okay, so why am I saying this? So you look at those two remainders, R1 and R2. Either R1 is greater or equal to R2 or R2 is greater or equal to R1. Okay, so, but let's say that R1 is the smaller one. Okay, but M divides A minus B or M divides B minus A, I can choose whichever one I want. So I can put them in the order I want. That's the point. Okay, so I just want to do my subtraction in the right order. Okay, so I'm saying it doesn't matter because I'm rambling. Sorry. Okay, all right. So hopefully this is okay. If not, ask me. Think about it and ask me. Okay, so let's do this. Okay, so what is A minus B? A minus B is Q1M plus R1 minus Q2M plus R2, which is Q1 minus Q2 times M plus R1 minus R2. Yes? Okay. Now, again, if R1 minus R2 were negative, I'd just subtract them in the other direction so that I'd get this thing positive. Okay, so here I've got that R1 minus R2 is greater or equal to 0. And I claim that it is less than M. Hopefully you believe that. Why is that? Because R1 is less than M, and I'm removing something from it. So this has still to be less than M. So that's, since R1 is less than M already. Okay. So then you can use my lemma, right? So by the lemma, M divides A minus B precisely when this remainder is 0. Because this is the unique remainder in the division algorithm, right? So we're done. And I know I've lost many of you. I know it. And so what we can do now is you can ask me what happened. If something didn't happen, just let me know where you were stuck. I can unstuck you, hopefully. You're all watching YouTube, I know. Yeah. Yep.
How'd you get to the last step? Like saying that R1 minus R2 is less than M. Therefore, M divides A minus B is equivalent.
Okay, yeah. That's it. Actually, that's a good point. I didn't write it. Okay, let me write this. Ooh, okay. So we'll have to skip here. Okay, so we've written A minus B as something times M plus this, which is between 0 and M. Okay, so this is, call that, let's say, Q prime and R prime, right? So by uniqueness in the division algorithm, I've expressed A minus B as QM plus R. And this must be the unique way of doing it, right? Because that R1 minus R2 is greater than 0 and less than M. So these are the Q and R of the division algorithm. Do you understand what I'm saying?
Yeah.
Okay. So the lemma, okay, careful, I'm going to scroll up. So if I go back to my lemma, it says that if I write a number like that, then D divides A, what I divided by divides A precisely when the remainder is 0. Okay, so I'm going to scroll back to the, okay, so with the lemma, and the lemma says that when I express a number this way, then M divides, so this is what this is the D in the lemma, M divides this number precisely when that remainder is 0. I know it's like a lot. You have to, once this is over, you have to take a piece of paper and you have to work it out a little bit by yourself. You have to go line by line, write stuff, do computations. You really, It's like learning a musical instrument. If you're just watching on YouTube, somebody tells you do this, do that, you're listening. It feels like, oh yeah, I can do that. But until you actually grab the instrument and try it, it's not going to work, right? So yeah, I know. So if you get it, that's wonderful. If you're not getting it yet, this is a good time to ask if I can unstuck you in one specific place for sure. And if not, then you'll have to, get into it by yourself later and then ask other questions. And okay. So again, I'm using this. I can write my number a minus b as something times m plus a remainder. And I've done that here, and it is the only way to do it. There is only a one way of doing it, and that has to be it, because r1 minus r2 is greater or equal to 0 and less than m. Okay. And my lemma says when you write a number like that, the m divides the number if and only if the remainder is 0. So I just write what that means in this context, and it means what I want, exactly what I want. Okay, so two numbers. So if you think in terms of the clock, two numbers are congruent mod m. So m divides their difference precisely when they fall exactly in the same place on the circle. Okay, so that's the gist of it. Okay, so a congruent to b mod m means a and b fall in the same spot on the m clock. Right, so if you look at, so for example, here's an example. Okay, let's say mod 6 question, is 17 congruent to 5 mod 6? Okay, so there are two ways of checking this. You can either, so that by definition, it means their difference should be divisible by 6. So this is if and not yes, if 6 divides 17 minus 5, which is 12, so yes, right? Or by the theorem, it means the same thing as the remainders when dividing by 6 should be the same. So let's do that. So let's write 5. With the division algorithm, it is 0 times 6 plus 5. That's the way to do it. It is the only way. What about 17? It's 2 times 6 plus 5. So yes, it's the same. So if you look on the clock, 0, 1, 2, 3, 4, 5. That's the 6 clock. They both end up here. If you're going around, you start at 0, you go around the circle until for as many steps as your number. So, right. So for 17, you'll go twice around plus 5. For 5, you just go to 5. Okay. You end up in the same place. Okay. So hopefully that helps to see it like that. Okay. Okay, I'm going to do one more result and then yeah, almost. I'm almost done for today. Okay, so next. Okay, so I'm going to skip one theorem in the book, which is theorem 4, which is basically just an observation, and I think I can do without it. So I'm just going to go to theorem 5. So again, I'm using the numbering from the book here, so you can connect. So this is a really fundamental result, and I'm going to try to explain why it's so important, because when I'm going to write it, you're just going to go, yeah, so what? but this is really fundamental. Okay, so I choose and fix a positive integer m. Like, think that's the clock we're working on, okay? And I'm going to play with 4 integers, a, b, c, and d. So our hypothesis is that a and b are congruent mod m, and c and d are congruent mod m. Okay, so what does that mean? It means m divides their difference, or if you prefer, their remainders are the same, or if you prefer, if you go on the clock, a times or b times, you end up in the same place. C times d times, you end up in the same place. Then the consequence is this, is that a plus c is congruent to b plus d mod m, and a times c is congruent to b times d mod m. Okay, before I show you why this is true, I'm just gonna try to briefly explain, and I'll after the proof, I'll also get back to that. But what does it say? It says that the remainders behave well with respect to the plus and the product. Okay, so that if two numbers have the same remainders and you use them in a sum, then nothing bad is going to happen to the remainders. Okay, that's essentially the big picture. Okay, this is the intuition behind this. It says that these congruences mod m behave well with respect to the two basic operations, plus and product. Okay, they do not behave well with respect to division in general. I'll get back to that. Okay, so let's try to prove this. Okay, the first one is easy. Actually, I could leave the first one as an exercise. It would be a legit exercise. Okay, the second one you'd have to it would be a hard exercise. Okay, so the product is a little trickier. Okay, so and I think I'm gonna show you a proof which is not the one in the book, so which I think is better. But anyway, let's do the first one. Okay, so I want to show that a plus c is congruent to b plus d. So I want to show that a plus c is congruent to b plus d mod m. Okay, what does that mean? It means that m divides their difference. Okay, so this means the same as m divides a minus b plus c minus d. Right, I just rewrote this differently. It's the same. So what I want to show is that m divides a minus b plus c minus d. What do I know? But m divides a minus b and m divides c minus d by hypothesis. So it has to divide the sum. Remember that very first thing I put on my whiteboard today is that if a number divides two numbers, it divides their sum, right? Okay, so see first slide. This is important, okay? So that first slide, that first little lemma said, if you have a number which divides two numbers, it divides any combination of those two. So you can multiply the two numbers by whatever you want, each of them, add them up, and your number will still divide that, okay? All right, so that's the first one. Hopefully you're okay with that. Okay, this is really the worst possible way of, I mean, we need a classroom and a blackboard to do that kind of stuff. If this is bad. Yeah. Okay. All right, Well, I'm doing the best I can. Okay, all right, second one. I want to show that M divides, so I want to show that AC is congruent to BD. So in other words, I want to show that M divides AC minus BD. What do we know? We know that M divides A minus B and M divides C minus D. So what the do we do with that? It doesn't look like, I mean, how do you combine A minus B and C minus D to get AC minus BD? Maybe find a way to, yes, that would, yeah, that would, in white. I can do that actually, but I'm not sure that's gonna do it. It's the physical presence of person talking to persons listening, which is really what's missing here. That's the key. I have absolutely zero body language feedback, you know. What the anyway. Okay, so how do I combine A minus B and C minus D to get AC minus BD? So here's a trick, which is cute, okay? And it's gonna look like I'm pulling a rabbit out of a hat, which to some extent I am, okay? But, okay. So what does this imply? It implies that M, so again, I said M divides these two numbers, so it divides any combination of those two numbers. I can multiply each one by the number I want, add everything up, and M will still divide that, okay? So my little lemma says that M will divide A times C minus D plus D times A minus B. I can do that, okay? Why am I doing that? You'll see in just a sec why I'm doing that. Maybe you can even see it almost now, what's going to happen. That's the trick, okay? So what is this? This is AC minus AD plus AD minus BD, which is exactly what I wanted. And we're happy. Rabbit out of a hat, okay? But this is a really classic trick. In one form or another, I remember seeing this in some advanced integral course in university in Lebesgue measure, and I remember it's a nice little trick. I mean, not quite exactly, but it's a similar trick. Okay, hopefully that works for you. So what does that mean? Okay, it means the following. Let me try to explain. So the meaning of this. Or the import, I should say. Okay, so you have your clock. And there are M different times on it. Here I chose, well, M is 8 here. Okay, now all the integers will fall somewhere on that circle. Let me draw this as follows. So imagine, so here we have 0 and then 1, 2, 3, 4. I could have chosen a smaller one, but anyway. 7, and then 8 will fall here, and then 9, and then 10, 11, 12, 13, 14, 15, and 16. So you see what I'm doing here. So all the numbers are going to fall somewhere. I didn't put the negatives, but okay. Oh, look, a flower. A flower? Okay, so what does this theorem say? It says that if you take some guy here and another one here, and maybe, so this would be your A, this would be your B, this would be your C, and this would be your D, okay? So it says that if you add A and C, you're going to end up in the same petal as B plus D. Okay, so if A plus C is here, then you know that B plus D is here. They're in the same, must be in the same petal. I'm making this up right now. This is not a real, okay? And the same for the product. A times C, maybe A times C is over here, and then B times D is over here, okay? So what's so great about that? Well, certainly one thing which is great about that is in terms of computations, this is very powerful because you see, if you have like two huge numbers to multiply, you don't need to multiply them. So let's just illustrate this in very simple. So think you are asked in which petal the product of two huge numbers, let's say A and C, is. Okay, so you have these two big numbers, and you want to know where the product ends up on this flower, on this clock. Okay, what this theorem says is you don't have to multiply them together. All you have to do is multiply their remainders. Okay, so theorem says multiply the remainders and you'll know. And the remainders are numbers between 0 and 7. So these are they're very small, right? So you have two numbers to multiply. Okay, you have to find the remainders. You have these big numbers, you have to find the remainder, but this is easy. Okay, and presumably you might know already what they are. Okay, so let's say one remainder is 2 and the other one is 3. 2 times 3 is 6. So you know that this huge product will fall in the petal 6. So you don't need to multiply them, and you know where it's going to be. Okay, so that's one aspect of this theorem, which is hopefully understandable and justifies it. Okay, so let me finish with arithmetic mod M. It's going to take me just 5 minutes. So let's do this. Okay, so we're going to define some new sums and products, which you've never seen before, but they're very similar to the one that you know. These are your first possibly new algebraic structures. There are zillions of all sorts of different algebraic structures available to us all over the place. And the ones you know are R, Q, and Z, and N. But these are like the first new ones, perhaps. Okay, so I'm just going to fix some positive integer. In fact, should be at least 2 for this to be interesting. And I'm going to define something that I'm going to call Zm, which is my remainders, 0, 1, right up to m minus 1. These are my hours on my m clock, if you wish. Okay, so I'm going to call that Zm. Okay, and I'm going to define 2 operations. On Zm. Now, this is not totally related to what we were doing just a minute ago. I mean, it's related, but this I could do what I'm doing now without the theorem. Okay, the theorem it connects what happens in the integers and in these small finite structures. Okay, so here are my 2 operations. So I'm going to define a kind of plus and a kind of product. Okay, so here we go. So for all A and B in Zm, I'm going to define a plus. And because it's not the usual plus, I'm going to put a little index M like that. So it's a new symbol. It's plus index M. Okay. And I define it to be what? Okay. So you add A and B the normal way, and you want to come back in Zm. So you take the remainder of that. So it's going to be A plus B. Take the remainder. That's the mod function. Mod M is the remainder of the normal sum. Okay. So this has to come back into Zm. So you take any two numbers in Zm, you get a new number in Zm. Okay. That's the plus. We have also a product, which is A times, and I'm going to put a little M here because it's not the usual product. But how do you do it? You multiply and you take the remainder. You take the normal product and you take the remainder like that. Okay, so these are operations on this set. Okay, it turns out, okay, so let me just show you a few examples and then I'll go a little further in the book, I think, in trying to give you an idea of what these do. So this is what you might call clockwork arithmetic. So you're basically working on this circle. Okay. So here's an example. I'm going to take m equals to 11. Okay. So I'm in Z11. You can see it on the circle like that. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ooh, yes. Right? So it's 0 to 10. So how does this work? So let's say I'm asked to compute 7 plus 9 in this thing. So what I do is 7 plus 9, which is 16, reduce mod 11, right? So this is 16 mod 11, which is 5, right? So that's the answer. That's the sum of 7 and 9 in Z11. It is 5. Another way of seeing it is that you're just going around the circle, right? So you start at 0 and you go 7 steps, and then you go 9 steps. 1, 2, 3, 4, 5, 6, 7, 8, 9. So you're going to end up at 5. That's the other way of seeing it. So you're just working on this circle all the time. You go around, right? Okay. What about a product? 7 times, but in Z11, 7 times 9. Okay, so the definition is you just do the normal multiplication, that's 63, but then you reduce mod 11. So here's how I do it. And I'm going to show you some tricks, not next week, next week, the other week after. I'm going to show you some useful tricks when you're doing these computations. But here I see 63 mod 11. I'm thinking, what's the closest multiple of 11 to 63? It is 66, and it's minus 3. So this is minus 3 on my circle. If you look on the circle, what is minus 3? It is 8, right? So this is 8. And in fact, 7 times 9 is exactly that. You do 7 around the circle, you do it 9 times, and you're going to end up in 8. That's what this says. Okay, so if you go 7 steps 9 times around the circle, you end up in 8. Okay, that's another way of seeing it. That's exactly what this says. Okay, because we're taking all the integers, we're wrapping them up on the circle. Okay. Okay. Very briefly, last thing I want to say, which is a bit out of the scope here, but if you look at Zn with this sum, Zm, sorry, with the sum and product together with the 0 in here, and there's a 1 also, right? So 0 and 1 are present in there. So this is a structure which is very, very similar to Z. It behaves almost the same as Z. So this behaves in many ways exactly like Z. Okay. Associativity, distributivity, all these things are all good. Okay. The big advantage, especially if you think of it in terms of a computer, computers are finite things. They cannot do infinite things. It's not possible. Okay. But ZM is like Z, but it's finite. So in theory, a computer can handle this, and it does. You can handle this very, very easily. Okay. So that's one advantage of these little beasts there. So yeah, and they are finite. They are finite, which is a good thing to have. Okay, so these are called rings. But anyway, and some of these guys are even better than that. So if you take M to be a prime number, then these are like Ferrari of algebraic structures. They are fields, better than the integers. So if M is prime, then it's what we call a field, just like the rationals or the reals or the complex numbers. It means you can divide, which is not the case if M is not a prime. But and these are like incredibly powerful, useful things. Okay, but that's another story. Okay, questions, comments? You've been doing linear algebra. All the linear algebra that you've been doing, you're doing on the real numbers. You can do it also on the rational numbers or on these guys, ZP. Linear algebra on ZP is kind of cool. Everything is finite, but it behaves like the real numbers. You can do Gaussian elimination. You can all do these things, but everything is finite. And they're used in codes. So there's a probe right now today on Mars, and it's sending information, and there's a lot of background noise. There's actually lots of cosmic rays and all that. So the information that's being transmitted has to be encoded so that we can actually correct the errors. And these guys are used like at every step of the way. Yes, that's another story. So there's a different kind of encryption than to keep things secret. It's a different story. Yeah. Okay. So if there are no questions, if you have questions on your own test, I will stick around. Let's remove this. Let's go like that. Let's stop the recording.